Let us look at rotational dynamics. So just a reminder, dynamics has to do with forces that cause an object to move, and in this case, it's forces that cause objects to rotate. So if a force acts on an object at a point that is not the center of mass of the object, then that object can rotate. We say that that object acquired a torque, and that torque is equal to the cross product between something we call the lever arm, L, and the force that acts on the object. If I have, for instance, a beam like this, so it has a center of mass somewhere here, and a force acts on it, if it acts at the center of mass, then the beam will move up in this direction with an acceleration that is proportional to the force and inversely proportional to the mass of the object. But if I have the same beam, here's the center of mass, and the force is applied somewhere other than the center of mass, then this beam might rotate like this. And then we'll say that the beam acquired a torque, and that torque is equal to the cross product between the lever arm, so that is the distance between the axis of rotation possibly here, and the place where the force acts. Now, I was uncertain what to say about the lever arm because I didn't initially choose an axis of rotation. So whenever we solve problems where we're dealing with torques, we first decide where we want the axis of rotation to be. If the axis of rotation is the center of mass, then this is the lever arm. But there are some other convenient places for choosing axes of rotation. So here would also be an appropriate axis of rotation anywhere along this beam where we would think that it's convenient to choose that. And we'll see that in problems in different videos. So here, this could have been the lever arm L, or this could be the lever arm L, depending on the situation where we want to pick this. But if I said that I want to choose the center of mass, I was looking at the center of mass before, then the rotation will be about the center of mass, and the torque is then lever arm crossed into the force, and a cross product is actually equal to the magnitude of the lever arm times the magnitude of the force times sine of the angle between them. So that's the magnitude of the torque. And the direction is the one that I illustrated here. This object will rotate in that direction. So here we have the magnitude of the torque. As I said, it's the product between the magnitudes of the lever arm and force, and also the sine of the angle between the two. Now, by convention, a counterclockwise rotation is a positive torque and a clockwise rotation is a negative torque. So back to my beam here, I'm going to pin it here. If I exert a force on it like that, here is my force, then I can imagine that this beam will rotate this way as a result of that force, and this would be the torque, and since it's a counterclockwise rotation, then it has a positive direction by convention. Now also look at the fact that I have this force now broken up into components, so there's going to be let's say an Fy and an Fx, and I had chosen this to be my angle theta. The only component here that causes a rotation is the y component. You'd have to push perpendicular to this beam for the object to rotate like this. Pushing along the beam, either pulling or pushing in, will not cause a rotation. So that's where this sine theta comes from. The y component here goes with a sine theta, and that's how this equation was derived. If we have an object that now we're saying is in equilibrium, there are two conditions for it. Before, when we dealt with linear dynamics, we said that the sum of the forces had to be zero because the acceleration is zero. So an object is in equilibrium if its acceleration is zero. But now we know that there's also angular acceleration, and we say that the object is in equilibrium if the torque is zero as well. So there is no net torque acting on the object. It doesn't cause a rotation that changes the angular acceleration of the object. So how does that impact Newton's second law? Let's say that we have an object like this, and there is a force acting tangentially to it. So you can think of a bicycle wheel being pushed up like this. Then the torque, by the definition, is going to be the lever arm. So the object will rotate about here, so that makes this the lever arm, the point between where the force is applied and the axis of rotation. So the lever arm is just R times the force times the sine of the angle between them. So the angle between the force and the lever arm is 90 degrees, and that's because any tangential line to a circle is going to be perpendicular to the radius at that point. Now, I'll rewrite this. I'm going to skip the sine 90 because that's equal to 1. So we have the radius, and by Newton's second law, the tangential force is mass times acceleration. And I can write acceleration as r times alpha. So then this becomes mr squared alpha. And if I compare this to F equals ma, I see that these two quantities stand for the acceleration. One is angular and one is just linear. And these two quantities have to do with the mass of the object. In particular here, it has to do with how the mass of the object is distributed about the axis of rotation. So we like to rewrite this as torque equals I alpha when we set mr squared equal to this I, and that we call the moment of inertia of the object. So this then becomes Newton's second law for rotation. Torque equals I fish. So here we have a neater expression here. So some of the torques acting on an object, there can be multiple forces acting on the object, giving the object a rotation. So some of the torques is moment of inertia times angular acceleration. Now the I equals mr squared that we developed here is actually the moment of inertia or rotational of inertia of a point mass that's rotating about a point r. We'll see that the moment of inertia depends on how the mass of the object is distributed about the axis of rotation. So different shapes of objects have different moments of inertia. For instance, if I have a baton that I want to twirl, if I twirl it about the center of mass, it is a lot easier to set it in rotation than if I try to turn it by its end. So the moment of inertia about the center of mass is 1/12 mass of the baton L squared, where L is the entire length of the baton. In the case where we want to rotate it by the end, I is actually 1/3 ml squared. So it's 4 times as difficult to rotate the baton about its end than it is to rotate it about its center of mass. These are not equations that one would have to memorize. They are actually given in tables in textbooks. Another example, if we have just a hoop, then all the points along here, all the masses that this hoop is made out of, are equidistant from the center of the hoop. So then the moment of inertia for a hoop rotating about its center of mass is simply mr squared, because you have multiple point masses at the same distance r away. For a sphere, for a solid sphere, so this is solid, the moment of inertia is 2/5 mr squared. And we'll see later in problems how the moments of inertia impact the rotation of an object. Now, rotational work and energy are also impacted by this rotation. And we know that work was force cosine theta times r. So basically we wanted the force to be along the displacement, which is why we ended up with a cosine or a dot product for the work. Now, force for rotation corresponds to a torque and displacement to an angular displacement. So work for rotation now is torque times angular displacement. What about kinetic energy? So we know that kinetic energy is 1/2 mv squared. So I can rewrite this as 1/2 m, and instead of v, I will reuse omega r quantity squared. So that's the relationship between linear tangential velocity and angular velocity. So this will become 1/2 m r squared omega squared. But we've seen this quantity before, and we called it I, the moment of inertia. So then the rotational kinetic energy will be 1/2 I omega squared. So here we have a summary of these work and energy equations. Another quantity that's affected by rotation is momentum. So previously we had linear momentum being equal to mass times velocity. Now we'll have angular momentum L equal to the equivalent of mass, which is moment of inertia, times the equivalent of velocity, which is angular velocity. The symbol for angular momentum is L, and the units are kilogram meter squared per second. Just like linear momentum, angular momentum is also conserved. So we'll say that the total initial angular momentum before a collision equals the total angular momentum after a collision. Now here is a summary of all the rotational stuff that we've done. Here you have the physical quantities and their rotational counterparts. These are equations or expressions for linear physical quantities. These are rotational quantities, and this is the relationship between linear and rotational. So let's take a quick look. We started out with displacement, which we called delta x, and then we looked at angular displacement, delta theta, and the relationship between them is x is r theta. Then we took the derivative of the displacement to find the velocity. So velocity was dx dt, and we took the derivative of this angular displacement to find the angular velocity. So that is now d theta dt. The relationship between these two is the tangential velocity is the radius of the circular path times the angular velocity. Then we have the acceleration, which was the derivative with respect to time of velocity. So a is dv dt. Now, for rotation, we have angular acceleration is d omega dt. And the relationship between them is tangential acceleration is radius of the circular path times angular acceleration. So we see how the progression between these relationships goes with the derivatives, first derivative and second derivative here. Then another concept that we dealt with in linear terms was force. And now we know that if that force does not act at the center of mass of the object, it can cause a rotation and hence a torque. So the relationship between force and torque is the cross product between the lever arm, or the distance from where the force acts to the axis of rotation, and the force that causes the rotation. Then another concept was that of mass, or inertia, and now we're looking at the moment of inertia, or I, and for a point mass, we know that I is mass times distance from where the mass is located to the center of rotation, to the axis of rotation, squared. Then Newton's second law said that sum of the forces is mass times acceleration, and for rotation, sum of the torques is moment of inertia times angular acceleration. Work was the dot product between force and displacement, or force displacement times cosine theta. Rotational work is torque times angular displacement. Kinetic energy was 1/2 mv squared. Rotational kinetic energy is 1/2 times m and v counterparts in rotational variables, so it's I times omega squared. Then linear momentum was P is mv. Angular momentum is moment of inertia times angular velocity, and there is a relationship between them. So the angular momentum is actually the cross product between the lever arm and the momentum. So it's displacement times momentum times sine theta, and this looks very similar to what we had for torque. So torque was RF sine theta, angular momentum is RP sine theta. So there is a relationship between these two equations. And then one really powerful concept was that of conservation of momentum, and we had that the sum of the momenta before a collision was equal to the sum of the momenta after the collision. That is also true for angular momentum. So before a collision and after the collision, the two net angular momenta are the same. So this basically summarizes rotational quantities.